Hello and welcome to the video about applications of exponential functions. We're going to talk about exponential growth and decay. We're going to talk about evaluating exponential functions with base e and some compound interest formulas. Let's go ahead and get started. All right, so exponential growth and decay is a very popular application for exponential functions. The formula for exponential growth or decay is a of t equals p times 1 plus r to the t, where p is the initial value, people think principal, the starting value, r is your constant percentage change, and t is time. So when we look at this formula, we can see that if r is larger than 0, we're going to have 100% plus whatever percent more, and it's going to be increasing. And if r is less than 0, we're going to be 1 minus some percentage, and we're going to be taking lesser than 100% each time. So we're going to do examples of both growth and decay. All right, so let's go ahead and look at the first problem and apply this. All right, tuition and fees at Oregon State University is currently $13,494 per academic year. If tuition increases 5% per year, predict the tuition in 4 years. So let's go ahead and fill out our parameters first. So our initial value, P, is $13,494. That's where we're starting from. Our constant percentage change is 5%. As a decimal, 0.05, and t, the time, is 4 years. All right, so let's go ahead and plug this into a of t. So we're looking for a of 4 in this case, is 13,494, 1 plus 0.05 to the 4 power. And we're going to go ahead and use our calculator to calculate this. I'm going to go ahead and bring up a calculator. I think I have one in my other window here. Let's see if I can get these both going. This might be useful anyway. I do not know what I just did. All right, so here's a little calculator I have up on the side. Let's go ahead and calculate 13,494 times 1 plus 0.05 to the 4. Now, this calculator is just the Desmos online scientific calculator, and it can take a whole argument at a time. But when you're calculating these, it's a pretty good idea to first do the 1.05 part. So I'm going to do this a piece at a time. So I'm going to go 13. Okay. All right, here I have my Desmos scientific calculator up here at the left. And I'm going to go ahead and calculate this value, 13,494 times 1 plus 0.05 to the 4th power. All right, so I got 16,402.04. Now, if you're using a calculator that isn't a scientific calculator like this one that can take a whole line of information at a time, some scientific calculators can only do one operation at a time. Make sure you're doing this correctly. If you were doing this one operation at a time, you would have to use order of operations. So the first thing you would do would be add in the parentheses, 1 plus 0.05. Then you would raise that to the 4th power, and you would multiply that by 13,494. So let me show you what that would look like if you were using a calculator that can't do more than one operation at a time. So the first thing I would do would be, well, and you probably don't need a calculator to add 1 to 0.05, but 1 plus 0.05. So that would be my first thing. Then I would take that number, 1.05, to the 4th power. And then finally, I would do my multiply by my order of operations, 13,494 times this previous value, 1.21550,625. And you see, either way, I come up with the same answer, but that's how you use a calculator that doesn't do one whole line of calculations at a time. So let's go ahead and write 16,1402.04. 16,1402.04. All right, let's try another problem. All right, the exponential decay problem. The town of Bobsville has been losing population every year since the year 2000 when a new settlement opened up in Sunflower Valley. The population in 2000 was 212,000. By 2001, the population was down to 206,700 people. If we assume the population is decreasing exponentially, find a model that gives us the population of Bobsville as a function of years since 2000. Predict how many people live in Bobsville in the year 2027. All right, let's go ahead and rewrite down our model, and I want to make sure I use exactly the same. A of t equals P 1 plus R to the t. All right, and let's go ahead and try and solve this problem. Well, let's start out by what we know. All right, so we want to find a model that gives the population of Bobsville as a function of years since 2000. So that's going to tell me what my t is going to be years since 2000. You don't want to start with t equal to 2000 because when you put that in exponential, it's really going to be a really large number. So my t is years since 2000, and my a of t is going to be my population. Right. And what do we know? We know the population in 2000 was we know the population in the year 2000 was 212,000. So this tells me that a of 0 equals 212,000. And we know about exponential functions, so we know that's going to be the starting value. So let's go ahead and just plug that in. A of 0 is also my p, 1 plus r to the 0. So anything to the 0 is 1, so this just gives me p. So p is 212,000. So now my model looks like A of t equals 212,000, 1 plus r to the t. All right, so now I need to figure out my r value. Well, I got some more information. I know that in 2001, the population was down to 206,700. So let's put in that point. That tells me that A at 1 was 206,700. And these type of problems are always going to have a find the initial, find the rate. You have to have 2 bits of information to find the value of these 2 different parameters. But it's also equal to 212,000. Oops, I meant to write 1,000. One plus r to the 1. All right, so now I need to solve this equation for r. 1 plus r to the 1 is just 1 plus r, so that makes that easy. Let's just rewrite that. 206,700 equals 21200 times 1 plus r. So the first thing I'm going to do is divide by 212,000. And that tells me that 1 plus r, and let's just grab my calculator really quick. Let's put in what was it? I had already lost the first number. Oh, dang, wrong button. 206,700 divided by 212. $206,700 divided by 212 equals 0.975. All right, so I come back to my here and I put 0.975 equals 1 plus r. So I subtract 1 from each side to get my value for r. And that tells me r equals 0.975 minus 1 is negative 0.025. Just to make sure, let's just go ahead and subtract 1 from that in our calculator. I don't trust my calculations. What am I hitting here? Oh, here we go. 0.975 minus 1 is negative 0.025, which is what I have. Perfect. So now we have our full model. A of t equals 212,000, 1 plus negative 0.025 to the t. And what we can see is we simplify this a little bit if you want to. We know what this number is. This means it is decreasing at a rate of 2.5% per year. So we have our 100% minus our 2.5% per year, and that means it retains 97.5% per year. So we can actually, to make this model a little bit easier to use, write this as 0.975 to the t. But we're remembering that this is exponential decay because we're not retaining 100%. We're only retaining 97.5% of our previous year's amount. All right, so I think we did the first part of this problem. It said, find a model that gives the population of Bobsville as a function of years since 2000. Great, we did that. Now, predict how many people will live in Bobsville in the year 2027. So we need to use the model now. If we're thinking about 2027 and t is years since 2000, that makes t equal to 27. So what we need to do is come down here and find the population at year 27. So that's going to be 212,000, 0.975 to the 27th power. And we'll use our calculator to help with that, I think. So 212,000, 0.975 to the see, oh, here it is, to the 27th power. And we get 200, oh, I don't think I put in 27, there we go. We get 107,018.9 people, so let's go ahead and write that down. 107,070.170. I'm really bad at remembering numbers. 18.9. And so, of course, since this is people, we're going to say the population in 2027 is predicted to be 107,019 people. All right, let's keep going. All right, now let's start talking about compounding interest. So compounding is when you have an initial amount that's changing by a fixed percentage, so it's still exponential growth, but we add in interest more frequently. So what we do, like, let's go through just annual compounded interest. So I'm going to pull up my calculator here, and actually I think I'm going to do this off. Well, I'll do the first one on screen and then I'll do off because it's just a lot of clicking back and forth otherwise. All right, let's talk about compounding. Compounding is when you add interest of a bank account or whatever else you're interested in looking at the exponential growth, and you add that interest back into the account. So let's look at what happens when we compound interest. And what we're going to do is we're going to just start with compounding interest. We're going to have a bank account where we have $100. Oh my God, this is just terrible. Start over. All right, let's talk about compounding. We're going to investigate a couple different scenarios here. It says 3, but we're actually just going to do 2. So make that number be 2. And we're going to think about what happens if we invest $100 in a bank account that earns 5% interest. And in our first example, we're going to add that interest in. We're going to compound that interest or add it to the principal just once a year. So this means we start it with $100. And at the end of 1 year, we have $100 plus 5% of $100. Well, that's going to be this is going to be $100 plus 100 times 0.05 is 5. And so that's going to be $105. So that means the second year, when we go to compound the interest, well, our principal starting that year was $105. Plus, we make interest on that $105. So our amount at the end of that year is 105 plus whatever 0.05 times 105 is. 105 times 0.05. So that's $5.25. So we made $5.25 in interest in the second year. We only made $5 the first, and that gets us to $110.25. Let's keep going. So year 3, we have $110.25 plus we earn 5% interest on that $110.25. 110.25 plus, that's going to be let's do 110.25 times 0.05 is $5.50. We're going to round to 551, which is going to be $115.76. So that year 3, we earned $5.51 of interest. And this makes sense because each year we earn a little more interest because we have a little bit more money in the account. Let's just keep going. Just going to do 2 more years. So why don't you pause the video and calculate these last 2 years, and then I'll do the same. All right, are you back? Did you get the same values as me? So for year 4, I saw that our value was at $121.55, and in year 5, I got $127.63. So each year I earned interest a little bit more because I had a little bit more principal. All right, now for our second example, we're going to compare what happens when we compound the interest more frequently. So we're going to compound the interest twice a year in this example instead of just once at the end of the year. So we still start with the same $100, and then 6 months in, we're going to compound our interest. So that is going to be $100 plus 100 times 0.05, and we have to divide it by 2 because the 0.05 is an annual interest rate, and we're doing it half a year, so half of a year would be divided by 2. So I'm off screen calculating this because I'm tired of flipping back and forth with my calculator. And I get 102.50, so you can do this along with me on your calculators. So halfway through the year, we compound the interest, and halfway through the year, our balance is now $102.50. So at the end of the year, another 6 months, we're going to do the same thing. So we take 102 and add to that 102.50. Plus 102.50 times 0.05 divided by 2, and we get 105.51. So comparative-wise, we made 51 more cents of interest in the first year. So when we compounded it once, we made $5 of interest, and when we compounded it twice, we made $5.51 of interest. So let's follow along a couple more years with this. So now we're going to do 105.51 plus 105.51 times 0.05 over 2. And we get 108.15. And then we do 108.15 plus 108.15 times 0.05 to the 2. And we get 110.85. All right, let's just keep going. So I would like you guys to pause the video. I'm going to jump ahead and fill in these last couple of values and go quickly through this, and then we'll compare at the end. Okay, great. All right, so we've computed all the rest of the values, and now we can compare what happened at the end of 5 years. And we can see by compounding it twice a year, we made $28.56 in interest. And compounding it just once a year, we made $27.63. And you'll see that pattern continue. The more frequently you compound, the more money that you're going to make. Well, we don't have to do this by hand over and over again. We actually have a formula for this. So here's our formula for compound interest. This will be another good one right now to go ahead and write in your note card. You're going to need it. And this tells you the amount of money you have if you invest P dollars, so P is your principal, at an interest rate of R written in decimal form in compoundings per year for T years. And just to go over the number of compoundings per year in case you aren't familiar with these words, annually is once a year, so N would be 1. Semi-annually or biannually is 2. Quarterly is 4. Monthly is 12. And weekly is 52. So let's practice using this formula without having to calculate it compound period at a time. We deposit $10,000 into a savings account that earns an annual rate of 2.75% interest that is calculated and compounded monthly. Find the amount in the account after 10 years. So let's fill in the values of our parameters. So the principal is $10,000. Okay. The interest rate, annual interest rate is 2.75%. So as a decimal, we move that 2 places, 0.0275. T is 10 years. And in number of compoundings, it says monthly, so that means we compound it 12 times a year. So plugging that into our formula, we have A of 10 years equals 10,000. 1 plus 0.0275 over 12 to the 12 times 10. So that's just plugging it into the formula. When you go to calculate this, you do have to remember to use order of operations carefully. So that means that you have to do this division first and this multiplication first because it's up in the exponent. So if you wanted to do this, being careful, if you have a calculator that doesn't take one whole line in, then you need to first calculate 0.0275 divided by 12. And that is 1 plus, and I'm just going to go 0.0022967. And you want to use a lot of decimals on that, just because when you're doing exponential, the error can really can grow exponentially. And 12 times 10 is 120. So now in my calculator, I'm going to do 10,000. Oops, that looks really terrible. Hang on. Let me fix that. And then I'm going to calculate 1.0022967 to the 120th power. So 1.0022967 to the 120th power. It's going to be a crazy number. I got 10,000, and that turned out to be 1.316117. I multiply that by 10,000. And I get $161.17. So my final amount that I would have, it would be $13,161.17. A little bit of a sanity check here. If you calculated this wrong and you end up with, first of all, something less than $10,000, you know you're wrong because you're investing money, so you should have more than $10,000. And if you invested at 2.75% and you ended up with like $131,000, you should know that that's probably way too much. So just make sure the final answer you get for these makes sense in the context of the problem. All right, and the last thing we're going to be talking about now is continuously compounding. So there is this number E. It is an irrational number, so it's a number sort of like pi that goes on and on and on. It's on your calculators, and it's about equal to 2.72. And if we let interest compound continuously, so not once a month, not once a day, not once a minute, like immediately compounding, and you take the limit of that value, it would turn into this formula, PE to the RT. And so let's practice using this continuously compounded. So whenever you see the phrase continuous, you should know to use this formula. Okay, it's very similar. You just use that value E. So let's do the same problem again, but let's say we have continuous compounding instead of monthly. Oh my goodness, I keep dropping stuff here. All right, let's do the same problem again, and this time we're going to do continuous compounding instead of monthly. So same values. We have P is 10,000. R is 0.0275. T is still 10 years. And we know the number of compoundings is infinite, so we're going to use this little e. So we plug it in and we get a of 10 equals 10,000 e to the 0.0275 times 10. Let me go ahead and pull up a calculator here so we can practice using the value e. All right, so here's my Desmos scientific calculator. And you will see that I'm going to put in 10,000. And now I need to get e. So if I go to function, I'll find it says e to the x. That's what you're looking for. Whatever calculator you're using is going to have some e to the x function. We want to pull up that e and then put our exponent up in that x part. So e to the 0.0275 times 10. Now be careful because I made a mistake just there. I'm going to leave that. What happened was the 0.0275 is in the exponent, but the 10 isn't. So I need to back that up and fix that. And the way I fix that is by using parentheses. So I'm going to put in a parentheses, and then I put 0.0275 times 10 in parentheses, so that keeps it all in the exponent. And it tells me the final balance will be 13,165.30. All right, so comparing that to my previous value, which was 13,161.17, I mean, I made about $4 more, so that's not too bad.